Good afternoon, I am Mr. Ish. You are joining me for this video. We're looking here at an introductory video on this cylindrical shells technique. It's a relatively difficult topic. Think back to the video I've done on introduction of curves and volumes where we talked about discs and washers. This right here is slightly a step above in terms of difficulty when compared to those other two techniques. Look at this x square curve from a 0 to 1 domain. You're looking here at this area below the curve along that domain. If you rotate this around the x-axis, you get a pretty good solid and a sideways cone which has a certain dimension to it, and you could easily calculate the volume of this rotational solid. When you take out a cross-sectional slice, you look at this slice from a side angle, you know you're looking at what appears to be a circle but a disc. It has a circular cross section, and we have a disc. It has a radius, and this disc has a certain area. You can call that pi or square. If the radius here happen to be x, this area with regards to x can become pi x square. When you're looking at volumes, you're integrating a given area of a cross section from a lower limit up to this upper limit, or you can say lower limit to a higher limit. We'll just say 0 to x. When you take these cross-sectional slice areas and you integrate them over this limit, you add up all of those resulting areas, you get a cumulative effect. The area cumulatively adds up into a volume, and the formula looks something like this, and you have seen this. If you were to look at this ax which is being integrated, you could push the pi out as a constant or a coefficient from a lower limit to an upper limit. We could even have set a to b, but we're using 0 to x, and we have an x squared over here coming out from right here, and then dx. When you integrate this, you get a good volume. And something similar to this, we have the cylindrical shells. It's a step above this, but it is along the same basis. You'll be looking at the development and the understanding of cylindrical shells and how they can be integrated over your domain to give you a volume of a resulting solid. Keep in mind, for these types of techniques, the basic volume curve determinations using discs and washers, which I've shown in the previous video, and this cylindrical shell, they all lead to the same result or the numerical value for a volume of a solid. But if you were to look, and this is me explaining to you what the cylindrical shell technique is, if we had an x square curve and we limited it from 0 to 1, and you're looking at this area below the curve, and then you rotate this around the y-axis and you look at the resulting volume, you know you'd have something which would look like this. You'd have a good mirror reflection develop over here, and you would have a volume that would develop for a solid, and it would look like this. You have a bowl-shaped concavity but surrounded circumferentially by this shaded area which goes around in a circular manner. You could very well easily do this cylindrical shell technique for this type of solid. You can do cylindrical shell for rotations about the y-axis, about x-axis, any horizontal, any vertical line. What's the basis for this technique? It's something to do with the Riemann sums. Look at only one side over here. If you were to draw just a rectangle over here, and then you were to rotate this rectangle around this line of axis, which is the y-axis, you would get something which would look like this. And we are drawing this rectangle here in 3 dimension, and you would have something which looks like this. 3 dimension. It looks like a cylindrical block, like a concrete cylindrical block. If you were to take this concrete cylindrical block and just pluck it out, it would look like exactly as I'm showing you, except here I'm showing you here from an angle, so it doesn't look circular, it looks more oblong, but it is really a true circle, and that's exactly what we're talking about. A circular cylindrical block. If you were to draw these rectangles from one end of the interval up to the other end, let's call that x, you could have an infinite or a finite number of these cylindrical shells which would very well tuck into one another from the start to finish. You would have the large cylindrical shells on the periphery, and then as you come towards the center, your line of axis, these cylindrical shells are small, just like stacking cups. Like kids play with stacking cup toys, you have these cylindrical shells which stack into one another from the largest going inward towards the smallest. If you take one of these cylindrical shells and you cut it and you slice it and then you open it apart, that is, you're stretching it out. The cylindrical shell actually turns out to be really nothing more than a rectangular prism. And this rectangular prism, when you look at it, it looks like this, a rectangular slab. This slab has a certain length, and you know you're seeing this length right here. This length is really nothing more than the circumference, which is 2 pi r of a circle. If you look at this outer periphery of this cylindrical shell, you know you're looking really at a circle. You're looking at it like this, like a donut-shaped circle, but we're looking here at this outer periphery. This outer periphery has a certain circumference. That right there represents the length of this slab as you've opened it up. This shell has been cut and opened up, stretched out into a rectangular prism, and that length is reminiscent of the circumference, which is your 2 pi r. Now this cylindrical slab, we can call it, has a certain thickness, and that's your delta x, which is your thickness. And there's a length, there's a thickness, and there's a little height component. We can call that f of x. When you look at all of these three components, you can actually bring all of these three components into a integral formula for a volume. Remember, you can do everything with respect to dx, everything with respect to dy. How do you bring the cylindrical shell into an integration formula? It's like this. You're gonna look at an integral from a lower to an upper limit. We're just saying x. We could have done a to b. You'll have a circumference component, which is your 2 pi x. Here the r is being substituted for x. You'll have a height component, which is your f of x. And then lastly, you'll have your thickness component, which is right here, my width. So you have three components coming into this formula: a circumference, a height, and a thickness. The thickness is easy. The thickness is either your dx or dy with regards to how you are integrating. This 2 pi x is your circumference. This f of x is your height. When you're doing these type of questions, you only have to figure out two things. You have to figure out the circumference and the height. And the height is no different than you determining the height of a Riemann rectangle, whether it was vertically oriented or horizontally oriented. The dx and the dy is all intuitive because you're basically determining with regards to your line of axis which way it will be. Now it flips a little bit over here. With regards to the washer and the disc technique, when you're looking at vertical lines of axis, y-axis, in the cylindrical shell technique, your integration will become with respect to dx. This is quite opposite compared to the other techniques. When you have vertical lines of rotation or axis or symmetry for the basic techniques, it's with dy, but with the cylindrical shell, it becomes dx. With the cylindrical shell technique, when you're looking at horizontal lines of axis or rotation, now it becomes dy, and you see that flip coming into play. Let's do a very quick digression and talk about this flip phenomenon that you see in the cylindrical shell technique. If you have a curve, we're just keeping everything very simple here, and it looks something like this, and we repeat that exact curve down here. For this top curve where you're seeing a linear line from 0 to 1, again on the bottom linear line 0 to 1, if you were to do rotation here on the y-axis for this top example, and for the lower one, rotation on the x-axis. Remember, the cylindrical shell technique requires you to imagine you're seeing Riemann rectangles which would be rotating or revolving. A rotation here on the y-axis, you're looking at vertically oriented Riemann rectangles, and when you look across from your line of axis, you're looking along the horizontal axis or horizontal direction, and you end up seeing movement along the x-axis. For this other example right here on the bottom, when you're doing a rotation now around the y-axis and you look across from your y-axis, the only way you can make your rectangles now are horizontally directed Riemann rectangles, which will then give you vertically oriented cylindrical shells. Here you'd have horizontally oriented cylindrical shells, here you'd have vertically oriented cylindrical shells. But here when you look at across and you're looking at this circumference formula, which is 2 pi r, but here in the top example the r is x. Here in the lower example, when you're looking up, you're looking along the y-axis dimension. Here you'd be seeing y come in as your radius. Hence, when you're having a vertical rotation or line of axis for a cylindrical shell technique, rotating along the y-axis, your formula becomes volume with respect to x, and then you do integration with respect to dx because you have x values popping here. Quite contrary to the disc and the washer method. Here in this lower example, you're doing rotation along the x-axis, but you end up seeing your cylindrical shell radii for the circumference are along the y-axis because at y values. Here you end up seeing a volume with respect to y and then dy, exact opposite of what you would normally think of. So you have to keep this peculiarity in mind. For cylindrical shells, vertical lines of rotation and axis give rise to integration with respect to dx. For the same technique, horizontal lines of axis and rotations give rise to volumes with respect to y and dy, integrations such as how I'm showing you right here in this exemplified manner. This is the flip phenomenon that you have to keep in mind for the cylindrical shell technique. We'll look at one good question over here with respect to dx because it will be a vertical line of rotation, and that question will be interesting. It'll be rather difficult, but again we're just introducing this concept. Let's look at this single question for this video, which will introduce us to this rather difficult technique. And the irony is we're using a relatively difficult example to introduce a difficult technique, but that's fine. We're just challenging ourselves. We have a function f of x is equal to sine x from an interval 0 to pi. We will rotate it or you can say revolve it, but truly it will be a rotation. We'll rotate it around the y-axis. If you think back to the disk technique, you know, if you were doing this around the y-axis, your formula would be volume with respect to y. You'd have vertically oriented intervals, let's just say C to D. You'd be looking from down to up would be your intervals, and you'd have an area with respect to y and dy. That would have been your disk technique or the washer technique. Now when you're doing the cylindrical shell technique for a rotation on a vertical line of axis in interval a to b, which will be along the horizontal dimension, you must determine a circumference component, a height component, and the thickness component. But the thickness component is already determined. How is it determined? Because we know we have a vertical line of rotation or a vertical line of axis, but we must flip it around and think opposite, and therefore we must do integration with respect to dx. So the thickness component is already done. All we have to do now is determine the circumference, and we have to determine the height of this function. You know, we're looking at a sine x from 0 to pi. My landmarks are 0, pi over 2, and pi. And you know, a sine curve goes no higher than positive 1. At sine of 90, it goes up to 1. Therefore, part of your sine curve looks like this. Let's focus here on the circumference component. The circumference component would be for any rectangle you can draw. Let's draw any rectangle over here. You can draw a finite or infinite number of rectangles. However many rectangles you can draw, from your line of rotation, which is your y, you will look across to any of these rectangles and you'll always be x units away. Any of these rectangles, if you were to rotate it around your line of axis, you would end up having a cylindrical shell. That's what a cylindrical shell would look like, generated from a single rectangle. And you know, this is what it looks like, but we have to just look at the formula here. We have to determine a circumference, we have to determine a height. We've already established from your line of rotation anywhere to any of these rectangles is your circumference radius, and that is x. You know the formula in all of these cases, the cylindrical shell always has a circular characteristic. It's always a 2 pi r. This right here, x value, represents your r, and this becomes 2 pi x. Now you have to determine the height. Anywhere along from this reference horizontal, for this specific case, looking upwards represents your height. And that height must be your sine x, because the sine x is always a certain number of units away from its horizontal axis, which here happens to be y equals 0. From y equals 0, anywhere you look at above or looking at down as you go through the rest of this curve, you will have a certain height, and that height will be sine x. So we have the components we need now. We have a circumference 2 pi x, we have a height sine x, we have a dx, which is our thickness. Let's show you what the solid would look like if you were to revolve the sine x around the y-axis, and let's try to draw it small. Drawing only the sine x from 0 to pi, you would get a mirror reflection on the other side, and then you know you have to revolve this around your y-axis. So let's eliminate some of these extra lines and get that rotational effect. You would have this develop here, you'd have something here going in the back. All of this area right here would be shaded because this is the region below the curve, the sine x, and then you know you're having this rotational effect come into play like this and then like that. And you can see what it looks like. You're going to have like a bowl shaped solid with an opening going inwards and closing into this inverted cone concavity, and it's going to be all open in here, but it'll be closed everywhere else. This is the volume of this solid that we're trying to determine using the cylindrical shell technique. So let's do it. We have our formula already at play over here. Volume with respect to x for this cylindrical shell is going to be from 0 to pi, the interval. We have a circumference 2 pi x, we have a height sine x, and then dx. Now the 2 pi is a constant, you can push it outside, or a coefficient 0 to pi. We have an x sine x dx. When you look at this right here, we have a product of two functions. You have to think about integrating by parts technique, and this is why you have to learn some of these techniques. You know you have uv minus integral v du formula you have to use. X here can be my u, then du must be dx, and then v must be the integral of what remains, which is sine x, and you know that becomes minus cosine x. To bring this into this formula right here, and you know all of this, we'll create this type of parentheses here, and then we'll bring the uv minus integral v du formula here. U is x, v is minus cosine x, and then minus v is a minus cosine x, du is a dx, and everything from pi up to 0. We can easily solve this in one step. We have a 2 pi, here we have a minus x cosine x, This minus minus becomes a positive cosine x. You're doing an integral of a positive cosine x, which is a positive sine x, and upper limit pi to 0. All you have to do is plug everything here properly to get to your volume. Remember, this right here is our volume with regards to x we're determining. You're going to plug the pi into places of x. You'll plug 0 into places of x. What we can do over here is create a good space and run this through. Let's do a 2 pi here and then create a large parentheses. Then let's create a smaller parentheses for the pi component. We'll have a minus pi cosine pi plus sine pi. This is my pi feeding into the x values. Now you do the difference. The upper limit values and now the lower limit values. You'll have a minus 0 because we have a 0 coming in places of x times a cosine of 0 plus a sine of 0. And we close this off. Cosine of 0 is a 1, but it gets zeroed out by this. Sine of 0 is a 0. All of this zeroes out. Essentially, what you're looking at is this right here. Sine of pi is a 0. Cosine pi is a minus 1. That minus 1 hits with this minus pi. You get a positive pi. That positive pi multiplies with this 2 pi, and your answer is 2 pi square. And you can do a numerical value here. Just do pi square on your calculator and multiply by 2, and you'll get a good numerical answer. And that would be the value for the volume of this rotational solid sine x over the interval 0 pi and rotated about the y-axis. It's a true rotational solid. So let's just put our value is 2 pi square, the volume of this rotational solid. And I've shown you what that solid looked like. And we utilize the cylindrical shell technique, a slightly rather complicated technique compared to the basic disc and washer method, but a very useful technique because there are some instances where the disc and the washer method will not work, but this can be used. Remember, I've shown you here only an example with regards to dx. A similar formula and workup plays out when you're looking with regards to y and dy. But that could be a material for another video. Thank you for watching. Have a nice day.